Tooth Cutting and Rotary Instruments. Part 1 of 2. Hi, I am Jenny, an ICE 50 avatar, and will present this exciting lecture. Angelo Caputo, PhD. And Tom Khalili, DMD, QME. Biomaterials Science Section. University of California, Los Angeles School of Dentistry. November 12, 2010. Multi-bladed instruments may be of two forms. Asterisk geometrically regular blades. Asterisk geometrically irregular blades. Burr cutting by flutes. Straight fissure carbide. Round carbide. Round carbide. Endodontic access. History of rotary instrument development. 1700s, hand-rotated instruments 100 to 300 rpm. 1942, diamond instruments. 1947, tungsten carbide. Today, air-bearing instruments at 800,000 rpm. Decreased sensitivity to vibration at frequencies of 1,000 cycles per second or higher. At 800,000, dentist loses tactile sense and can overcut tooth structure. Various hand pieces. Mechanics of cutting. Compressive, tensile, and shear stresses by an instrument that is harder than material to be cut, forms a chip to act as an abrasive. Cleavage or abrasion may be thought of as a series of high-speed stress-strain curves. The deformation occurring between cycles is retained energy, most in the form of heat, altering the physical properties. Smear layer. An amorphous layer 1 to 5 microns thick, firmly attached to the substrate. Formed by permanent deformation of tooth structure during cutting and abrasion. Burrs. Parts of burrs are head, neck, and shank. Head, tungsten, carbide, 10% cobalt, sintered, high pressure and temperature, vacuum. 5 basic shapes. Round, inverted cone, pear, straight fissure, and tapered fissure. Many variations have been developed as handpiece speeds changed. Head welded or brazed to the neck. Neck and shank. Neck, usually steel, narrow at the welded attachment to head. Head design. Important characteristics. Neck diameter. Head diameter. Head length. Taper angle. Blade spiral angle. Crosscut size. Spacing. Optimal values for the angles. Dependent on the mechanical properties of the material to be cut. The mechanical properties of the cutting tool. Speed of rotation of the burr. Diameter of the burr. Force placed on the burr. Factors affecting temperature rise in the pulp. Increased temperature may result in pulpal damage and expansion fractures. Force applied by operator. Size, shape and condition of cutting tool. Revolutions per minute. Duration of cutting time. Use of air and water spray to control temperature rise. Expansion fracture. Dentin as a good insulator. Heat of rotating burr in the cavity preparation. Concentration of heat in a limited area. Expansion with compressive stresses. Tensile stresses and propagation of cracks and fissures. Composition of enamel and dentin. Enamel, 92% hydroxyapatite, 6% water, 2% organic substance. Dentine, 47% hydroxyapatite, 30% organic substance, 23% water. Dr. Tom Khalili, ICE 50 founder states, I hope you enjoyed this lecture.